For the intersection control algorithm, research was first conducted to examine whether a V2V or V2I approach would be used. After considering factors such as the resources and infrastructure required, as well as algorithm simplicity, the final choice was a V2V algorithm. The advantages of this approach include dramatically lower infrastructure setup costs, especially at intersections, as well as better reliability because there won't be a single point of failure, which in a V2I scenario would be an RSU, which needs to process all intersection crossing requests from other vehicles. Numerous V2V intersection control papers were also examined when considering the design of our algorithm. In the end, we decided to use the Weimar algorithm as a foundation, which simulates traffic flow as a roundabout.
We will now explain at a high level how our algorithm behaves. The intersection control algorithm is split into three main sections. 1. Pre-intersection. The vehicle continuously scans its surroundings and broadcasts its own CAN messages to all surrounding vehicles in addition to receiving them as well. This allows vehicles to obtain information on the vehicles around it, including aspects such as position, speed, and intended direction. 2. At intersection. Once the vehicle arrives at the intersection, it will assess whether a collision will occur between it and other vehicles based on their intended paths. If there is no collision detected based on vehicle paths, then it will cross the intersection. If it detects a collision, it will slow down and stop if necessary. If it is the first road leader, then it will send a message to other road leaders seeking permission to cross. After receiving acknowledgement, then it will proceed to cross the intersection. Otherwise, if it is not the first road leader, then it should wait for the next closest road leader to give them permission to cross. 3. Mid-intersection. Once the vehicle has entered the intersection, it should check if it is the last vehicle on the road. If it is not the last vehicle on the road, it should send a handover message to the vehicles behind it to allow them to cross as well. Then it will continue through the intersection. If it is the last vehicle on the road, it will continue through the intersection before checking for any more road leaders. If there is another road leader, it sends an allow pass message to them. For the majority of the year, we have dedicated our time towards carefully designing our algorithm to ensure its safety, efficiency, and reliability. Through application of our algorithm on basic intersection scenarios, we have found that it is capable of managing multiple vehicles simultaneously. However, implementation of the algorithm in ROS has shown to be more difficult than we had anticipated. Due to the complex nature of the algorithm and its dependence on external data sources, both within the vehicle's other systems and messages to and from other vehicles, made for a complicated system to program. We are currently still in the process of programming the algorithm.
In terms of our plans for the future, we will continue to work on completing the intersection control algorithm in ROS, as well as integrating it with other systems. Further improvements to the algorithm can also be made so that we can extend its functionality and also handle more complex scenarios, such as ones where vehicles have multiple followers on the road, change of direction decisions, or error handling in the case of malfunctioning or malicious vehicles. Since the algorithm has been split into different parts based on the vehicle's distance to the intersection, changes should hopefully be more easy to implement.